Hey, differential equation students. We want to solve this differential equation here. On the left-hand side, we have what we've seen before from spring equations. Note that there is no damping constant. But on the right-hand side, we've got something new. That's the Dirac delta function that you've read about in the section for Wednesday. This means that we're going to give an impulse, think of this as a hammer hit, at time 5. So let's start solving this by doing Laplace. So we're going to Laplace here. We're going to get 4s squared, the Laplace transform of y, plus the Laplace transform of y. And now we've got our new formula whenever we have the Dirac delta function. When we Laplace it, we're going to get e to the negative 5, that's from that 5 right there, times s. And note that over here, because our initial conditions involve no motion, that we didn't have to do anything extra on the left-hand side. This is pretty easy to solve for. I'm going to keep the e to the negative 5s out in front, and we have this fraction. That fraction is not quite one of the forms that we're interested in, so I'm going to factor out a 1/4. So it starts with an s squared. Now it's looking a little bit better, but we still need to do a little bit of work to make this look like something we're comfortable with. We need an s squared plus a number squared, and that's going to be 1/2. And one last thing we need to do is we need to make sure that that 1/2 shows up on top as well. Well, the way we can think about it is we'll put 1/2 down here and 1/2 up on top. And together they multiply to give 1/4. All right, we are ready to take the inverse Laplace transform. So as usual, that e to the negative 5s turns into a heaviside function. In this case, u sub 5 of t times the inverse Laplace of this shifted. So we're going to have a 1/2. And what we have here is the Laplace transform of sine. In fact, it's sine of 1/2 from right there. And we have to account for the shift. So that's t minus 5. There's our solution. So you can tell what happens is we are going to turn on this sine function at time 5. We're not going to have anything happening before that, which makes sense because our initial conditions say we start at equilibrium with no velocity. All right, let me go ahead. Oops. Let me see if I can make this work. Hey, fantastic. There's the graph. Now, if you look at this graph, please notice what's going on here. You are seeing no motion for the first 5 time units. And then, boom, all of a sudden we start following the sine pattern. Now, notice that it's not nice and differentiable there. We don't see a nice curve increasing to the sine function. We see a hit. That's characteristic when we've got the Dirac delta function. So in other words, we expect to see, because we're using that, nothing happening for some time, and then boom, something happening. And that's a good example of how to solve a differential equation using the Dirac delta function.